So welcome to the Friday seminar. Today we have a special speaker, myself. So I'm running the seminar together with Liming Wang from Urban Planning. My name is Miguel Figliozzi from Civil Engineering. And today we're going to start with a bit of a theme related to data and applications of data in transportation. So today I'm going to be talking about data and multimodal transportation on Powell Boulevard. So this is a project we had together with the Transportation Center Utrecht and with the collaboration of the City of Portland and TriMet. So before I say anything, a lot of the content and a lot of the material here would not be here without the help from three of great research assistants that work in our transportation lab, Wei Feng, Eric Albright, and Courtney Slavin. So Courtney helped a lot with air quality and traffic evaluation. Wei Feng, is here, helped a lot with the transit evaluation. The same thing with Eric Albright. So thank you to them all. But anyway, any problem or mistake is my fault. It's not theirs. So a little bit about some background about what we were trying to do in this project. And this is kind of 101 traffic signals in 1 minute. So you can have different type of traffic signals, controls, when you're looking at an arterial like Powell Boulevard. So you can have fixed time, fixed cycle. Cycle length is the time it takes to go through all the approaches in the intersection. Or you could have what is the state of the art, that is adaptive. Adaptive traffic signals are those that they can measure what is going on in terms of vehicle demands in all the approaches, and then regulate the green times and the cycle length based on the demand that is happening, cycle to cycle. So the other option is you have pre-time throughout the day, maybe different signal times that you are changing. Say you can have an afternoon peak hour plan, a morning peak hour plan, and off-peak signal time, But those are not responsive. You only respond to historical patterns. You don't respond to more real-time, on-demand vehicle volumes, So, and there are different issues. Obviously, for adaptive, you need to measure what is going on in all the approaches. So you need to have loop detectors or any other means to know how many vehicles are going through. And you need to have more expensive software to coordinate all the traffic signals. And there might be also trade-offs in terms of maintenance and upkeeping the traffic signals. So calibrating adaptive systems can be very time-consuming because it's a very complex piece of software. But in the long run, it could be easier to maintain because then the system kind of regulates itself. With time of the day, pre-time signals, then you need to be checking if the demand volumes are changing over time. Because if they are changing, then you need to change the green times and so on. So you have pros and cons regarding the two. So one of the things about our project was on Powell Boulevard, there was this implementation of a state-of-the-art adaptive traffic signal that is called SCATS. So one of the things was, what's going to happen along Powell after we install SCATS? So, and these are not cheap investments, so you want to measure and to evaluate to see if the investment was worthwhile. So again, the idea about the SCATS, like any adaptive traffic signal, is you adjust the cycle length, the different phases, and the offsets to optimize traffic flow. Something else that is going on Powell, maybe you are not aware, is that we have a lot of buses running through Powell. So, and these buses also interact with the traffic signal system using something that is called transit signal priority. So when the buses are late, they can request a green extension or shorten the red time so buses that are late can recover and get back to their schedule. So one of the things about SCATS in the US was like, well, there was never a joint implementation of an adaptive traffic signal and transit signal priority, TSP. So one of the questions was, what's going to happen to the transit performance? Is it going to be beneficial? Is it going to be neutral? Or is it going to be maybe not good for transit? So that was one of the issues. And again, the city had to kind of deal with the vendor to make sure that signal priority was included, because in the original package, that was not one of the things that they were offering. So some of the goals of these adaptive signals usually is to be responsive to vehicle demands, and then to coordinate traffic flows, maintain the highest level of saturation, reducing overall delay, and so on. So one of the things, like there can be other goals, because like on Powell, you have multimodal usage. So usually transit, for example, is not a goal. And it could be like pedestrians, you know, delays for pedestrians or safety are not usually goals because they are not included in the traditional goals of an adaptive traffic signal. So just to give you the background, that is very vehicle-oriented and not considering the other modes. This is to give you an example. You can see here the two graphs. So here you have on the top volume per cycle from roughly 6:30 to 9:30. And then this is the total number of vehicles that are going through. And then you have the cycle length. And you see it's not perfect. There could be some trends. It kind of go up and down. But it's not a one-to-one correlation because you have a lot of constraints. So for example, you can have the maximum cycle length constraint. You could have pedestrian calls. You could have side street traffic that is requesting green. So it's a very complex kind of problem in terms of trying to allocate the green times. But the system, you know, with SCATS tries to be responsive, and you can see that here. Like I said, it's not perfect because there are many, many other constraints that have to be satisfied. Yeah. So we had 4 objectives. The first one was vehicle-related traffic. Can we notice any improvement before and after? The second one, what about transit? Can we see that the SCATS was positive, neutral, or negative for transit? The third one was related to TSP. Was there any interaction with TSP, or was SCATS allowing TSP to really be efficient? And the fourth one was related to impacts on air quality. So I'm going to go from 1 to 4 because it's roughly kind of going from the easy to the hardest. And I'm not going to have a lot of time to talk about air quality. I'm just going to give some highlights. But just to give you an idea, this is the order of the presentation. I will try to answer these 4 different objectives. So data was key. Without a lot of data, and we are very lucky in Portland that, you know, we have good data sources, and we needed a lot of data to be able to measure before and after. So in terms of traffic, we have Wavetronic radar detection units, so we can tell vehicle volumes and vehicle classifications at 2 locations along Powell. Then we had, after SCATS was implemented, the loop detectors. And then in terms of transit, we had great data. So we have all the logs from all the vehicles running through Powell in terms of not only location and time, but also boardings, analyzings, and so on. So we had a lot of good data regarding transit. And we had access to some TSP logs. So you can go to the traffic signal and download very specific, very detailed TSP calls. And then we had some air quality data. So we have to go and collect some air quality with our equipment to measure changes in air quality with different traffic volumes. So to give you an idea about the section we are talking about, so if you're familiar with Portland, you will recognize it's between the river and 205, and even smaller than that, between 10th and 86th Street. So roughly 5.1 miles. And then you have 14 signalized intersections in the segment we are studying, and 54 bus stops. So it kind of gives you an idea about how many traffic signals you have in these 5 miles. And again, this is an arterial, and it's the performance of Powell is very dependent on the time of the day, because in the morning you have a lot of traffic going to Portland downtown, and in the evening you have the opposite, a lot of traffic going to Gresham. So the peaks are very different in terms of direction in the morning and in the evening. To give you some numbers, peak hour westbound is in the morning, so going to Portland, around 1,700 vehicles per hour. Eastbound in the afternoon, around 1,800. So both directions daily, roughly 40,000 vehicles you have on Powell. So significant. It's a busy arterial. For a two-lane per direction arterial, it's a pretty high volume. And this is to give you an idea about how it changes over time throughout the day. So here you can see this is going to Gresham. So in this case, the peak is in the evening, in the afternoon. So here we have on the Y, here we have a speed in miles per hour, and then we have vehicle volumes per hour on the X-axis. So you can see, like, early in the morning, if you know Powell, the speed limit is 35 miles per hour. So the red dots, you would see that in the morning, going eastbound, you have a pretty good speed, and this is using Wavetronic data, so measuring volume and speed. So we see it's very good, the red dots, above even the speed limit. Then you see, like, between 10 and 1, the blue is kind of shifting down. So you're increasing the volume, and the speed starts to go down. Then you see between 1 and 4, you have the green dots, and then you see, like, going from kind of good speeds starting to go up to 25 miles per hour. And then we have 4 to 7, and you have the yellow dots. And you see that this is 25, 20, 15, even to 10 miles per hour. So the traffic really slows down once you get to this kind of beyond 1,400 vehicles per hour. It's a kind of starting to really queue up and kind of reaching capacity. So it's very clear that then after 7, the black dots, they go again up to the speed limit. So you see throughout the day this evolution that, normal cycle. And like I said, in a typical traffic signal system that is not adaptive, you would try to have different signal times for each one of these periods. But with adaptive, because the system is responding to the number of vehicles, then the system itself, the software is changing cycle by cycle the green times. So, and this is measuring the traffic speed between 35th and 36th. Yeah. So it's not at the traffic signal, it's in between traffic signals. That's why the vehicles are going close to the speed limit. So looking at the traffic evaluation, these are two nice graphs that looking at Powell and 26. And here we are trying to measure before and after SCATS what happened in terms of speeds before and after. So here we have the difference in terms of speed, and here we have the morning peak. And this is for the westbound. So remember, for the westbound, the morning peak is the worst time of the day. Yeah. And here we have the two bars, the blue before SCATS on average, and then the red bars after SCATS. So we see mostly throughout that after SCATS, we obtain, on average, higher speeds. And so anytime we have a positive here means that the vehicles are able to move faster during the peak time. So we can say that in terms of the implementation of SCATS really helped in terms of vehicle mobility, getting them to move faster. And one of the things you can achieve this is because maybe vehicles are not being stopped so much at the previous intersection. So vehicles are not hitting the red, so they can continue the green wave, and they don't have to stop. So that's why you might get higher speeds on average. Yeah. So, and that's kind of important because we want to provide progression. We don't want vehicles to stop, because with every stop we consume more fuel, we have more emissions, we decrease their quality, and we increase the delay for everybody. Yeah. So this was a nice thing to see. But if you remember the previous graph, you can tell that speeds are really dependent on the volume of vehicles. So just looking at this is not enough. We need to see if we were serving the same number of vehicles before and after. Because if we are serving less vehicles, then it's always easy to have higher speeds. Yeah. So we also look at volumes. And looking at volumes overall, we detected that after SCATS, it was good. We had more vehicles with higher speeds. So it was actually a win-win situation. So we're able to serve more vehicles. There were less stops at the intersections, and we're able to go faster. So, and you can see here again, this is difference. The green above 0 means there are more volumes throughout this period of time, and then negative meaning in those 15 minutes less. But overall, we had more vehicles and higher speeds. So actually, we could say that SCATS was beneficial in terms of improving vehicle mobility. So summarizing the traffic evaluation, so we had higher volumes, higher speeds on average. So we can say that the SCATS was good. And I'm just showing a tiny bit of the data and the tables, but in case you had the question, I want to say that we accounted for day of the week and other variables like weather conditions and so on to make sure that the comparison between the before and after was fair and meaningful. Yeah. So we're accounting for many variables to make sure that we can compare apples to apples, yeah, and come out with this conclusion. So going to traffic performance measures. So we look at different things like travel time along the corridor for buses. So what is the total time it takes to go from, like, say, 86 to 10th, or the other way around if you're going eastbound. And in this case, we had one point where it's like, we call it a time point reliability, where buses have to, we check against their schedule, and that was at 39th. And in all the results I'm going to present, we were also controlling for number of passengers before and after to make sure that there was not a significant difference, because, you know, the more passengers are boarding or aligning, the slower the bus is going to go. So we were controlling for that. The same with the number of stops. And then when we look at the TSP effectiveness, we're also looking at number of requests, time of the day, direction of travel, the bus maximum speed that kind of relates to traffic conditions, and so on. So there was a lot of data that we could use to make sure that the comparison was fair with the before and after. So some results, and so we had regression models, and I'm not going to show you big tables because we had like 20 sampling variables, so it's a huge statistical model that it will be impossible to read from the screen. So I'm just kind of showing you some overall results. So one of the key things that we noticed was that the performance before and after SCATS was really dependent on time of the day and direction of travel. So overall, we noticed that the SCATS was beneficial for transit. So we could say like 20 sampling seconds of gain, reducing transit time. But this is not spread out equally. And why? Well, you know, there are things we can speculate why this is happening, but, you know, it's very complex, and trying to understand what is happening with traffic at the different intersections, different directions. But overall, from the statistical models, we're able to notice these trends. Overall gains, but the gains were not spread out equally. And in the case of the westbound peak period, we noticed that it was worse. It was better in all other cases except in that case. So mixed positive results, but overall, on average, was positive, but again, mixed positive. So it really depends on the direction of travel and the time of the day. And in terms of on-time reliability, we had during off-peak improvements in a schedule delay in the westbound direction, and during peak, no improvements in the headway. So at least we were sure that it was not worse. So SCATS, at least we know that it was not a negative factor for transit. That was one of the things we really didn't know, because again, there is very little experience trying to mix the two systems. So a little bit about signal priority. So I'm not sure if you're familiar with this concept, but the idea is you have a bus, and a bus, you know, you can know if that bus is running behind schedule. And if that bus is late, there is an optical detector at the traffic signals that can receive a signal that goes from the meter from the bus that is late. And this late bus can be requesting priority. So requesting priority can be like, say, if the bus is approaching the intersection and is late, the green can be extended so the bus can go through. Yeah. So it's something that can be done so buses recover their schedule. So we know from our models and all the data, so we took months of data, and we look at before and after, and we look at TSP, no TSP, looking at routes with TSP, looking at routes without TSP, and then looking at before and after on Powell. And we can see that statistically, TSP does reduce travel time for buses and can facilitate schedule recovery. So those things were significant in terms of statistically significant. But there is something that is very tricky in terms of trying to measure from the data what is the impact of TSP, because in some cases when the bus is late, the driver itself knows that he's behind schedule, and he or she can try to go faster, not to delay so much, try to accelerate more, and so on. So we did account for that. It was a bit tricky, and there was comment from Steve Callas from TriMet, and he said that maybe we can look at the maximum speed of the bus between stops, and that could be a proxy for how fast was the driver trying to go and what speed was allowable for the traffic conditions at the time. So we accounted for that kind of what is the maximum speed that the bus can reach between stops. And in a way, incorporating that, even taking that into account, we're able to still notice that TSP buses that were late and requesting priority were going, saving some time. So there are other things that we notice, that TSP is not just, again, homogeneous or the same across intersections. There are many factors that can affect TSP, and here we have some. So we notice like intersections like, say, 39th or maybe Milwaukee that have more cross traffic, then it's harder for the buses maybe to get priority and to recover because, again, there is maybe not so much room to provide a green extension because the time is scarce at that intersection because there is too much traffic going on at the cross street. So we also noticed that, and this we still really don't understand how the bus bay length and the stop location in terms of near side or far side impacts TSP, but we know from the models that there is an influence. And for sure, we know that time of the day and direction of travel, like in all this study, that was really important. So TSP helps, but again, there are many, many factors kind of behind why it helps, and in what cases it can be useful or can really provide an advantage for late buses. So just trying to give some numbers to try to wrap this up. So roughly 5 miles, imagine like if you just take travel time, discounting all the slowing down for stops and the time of stops for passenger boarding and alighting and so on, between 500 and 700 seconds. But also you need to think that there is time of the day and direction effects. Yeah. So during peak times, it could be closer to 700, 750. During off-peak, could be closer to 500 seconds. But roughly on average, we can say that from our models that SCATS was helping 23 seconds, improving travel times. And TSP, roughly 2 seconds per intersection on average. Again, there are huge variations, but on average, you could say that a bus late hitting all the priority at all intersections could be up to 30 seconds. So roughly up to 10% of the travel time, just the pure travel time, not including the time at the stops, can be gained through the two systems. And just to give you a reference, like peak periods, like in the afternoon peak or morning peak on average, buses can be 1.5 minutes, 2 minutes, extra time to travel. So again, you have to give the kind of the big picture in terms of it was good that SCATS was not bad for transit, so that was a relief to know that was the case. So can you get too much of a good thing with TSP? And we did find that in some cases, TSP cannot be good for some things. So one of the things that happens with buses, and maybe is bus bunching, when two buses are too close, so you can see the two buses coming. And sometimes if the two buses are late, then they might both get the TSP and the priority. So it might be the case that in some cases, TSP doesn't help to separate the buses between the first one and the second one. Yeah. So that could be in some occasions, but again, overall TSP is good. I'm just saying that sometimes you can have these specific cases because it's very complex in terms of trying to control real-time buses. Another thing we discovered from our models is the travel time of one bus is really correlated with what's going on with the 3 previous buses in terms of number of passengers, stops, and so on. So it's not like just you can look at just one vehicle at a time and really try to understand everything about that vehicle. You cannot do that unless you take into account what happened to the 3 previous buses. Because whatever happened to the 3 previous buses in terms of how many passengers they were getting on board or alighting may affect what happens to this bus. So it's a kind of, that adds complexity to the analysis because, again, you cannot just look at pieces independently. So the other thing about TSP now is like it's kind of what we call myopic. It's just one bus at a time can request priority, but that bus that is requesting priority doesn't take into account like if there is another bus that is too close or too far away and so on. It's just one bus at a time, not taking the kind of the system view of the bus route. So just moving on from transit now to air quality. So I think this was quite unique, what we're trying to do in terms of not measuring emissions, because most studies, they would use models to say, well, there are so many vehicles, there is so much delay, so they are going to generate so much CO2, so much CO, and so on. So in our case, we're doing kind of sidewalk measurements with actual air quality equipment to see what were the changes in terms of CO, carbon monoxide, CO2, particulate matter, and ultrafine particles. So it was quite a different approach from most evaluations, and actually most evaluations don't even take into account air quality, so it was kind of quite different. So I don't have time to go through all the models, but we did see a significant and clear statistical relation between traffic volumes, vehicle types, queuing, and the duration of the phases at the traffic signal. So the amount of green that you give to the main Powell versus the secondary streets do have an impact on air quality at the sidewalk level. So overall, we saw that SCATS tends to improve air quality, at least at the points where we were measuring air quality. Why? Because the answer is, our hypothesis is like you have less queuing, so vehicles tend to be more efficient in terms of emissions per mile when they can go at, say, 30, 35 miles per hour, versus when they stop and they idle and they have to accelerate and they go at lower speeds. So having this kind of more constant speed profile really helps in terms of reducing emissions. And we did see that from our models. So one of the things like that was very interesting and we were able to see was that for some pollutants like particulate matter, so I don't know if you know much about PM, but tends to be generated by diesel engines and tends to be really bad for you when you breathe that, because there are very, very small particles. We're talking about microns that go into your lungs, and they can even go into your bloodstream. And even they are so small, some can cross the cell walls and get into cells. So it's really bad stuff that is linked to cancer and heart disease and respiratory conditions and so on. So one of the things we observed was that queuing and idling was really, really significant for this kind of pollutant. And for example, one heavy-duty, commercial vehicle or heavy-duty diesel engine in our models was equivalent to hundreds of passenger vehicles in terms of PM. In terms of, for example, CO, it could be 1-to-1, but in terms of PM, it was really, really significant. Some heavy vehicle factors, so we did notice, for example, thanks to the data that TriMet provided, that and from taking pictures at the different buses, that buses that had, for example, the tailpipe slightly angled away from the even more, some they have parallel to the sidewalk, some they have angled a little bit more away. Those were kind of having significant reductions of pollution at the sidewalk level, at the bus stop level, for example. The bus engine efficiency, so thanks to TriMet that provided this data, we were able to see that buses that had more efficient or add-ons to increase the efficiency of the engine will have less pollution. So the other thing that was very significant was, like I said before, idling. So if you have the red light and the bus cannot exit or any heavy vehicle cannot move, that idling is really bad in terms of air quality. So we're able to really show that kind of statistical significance. The other thing that we noticed was this kind of what we call in statistics lagged effect. So even if the vehicle was here 2 minutes ago, you can still feel the presence in terms of air quality. So it takes, depending on the wind condition and temperature, humidity, so atmospheric conditions at the time, but it could take some time. You cannot, maybe the vehicle is way gone, but you happen to be at that time, and then you will get the bad air quality. So some of the kind of conclusions in terms of wrapping up. So I think traditionally, and yesterday I went to an IT, so IT is Institute of Transportation Engineers, a kind of roundtable workshop talking about adaptive traffic signals, because there are a couple of systems in the region. And I think overall, the traditional goal has been to focus on vehicle movements, looking at street capacity, mobility, and I think we do a good job in terms of measuring improvements or changes in capacity mobility. In terms of looking at specific technologies and how to evaluate what is going on with the effectiveness of like technology, like say SCATS or TSP, it's much more difficult, so that's not done as much in terms of really detailed analysis. But in terms of accessibility and livability, you know, pedestrians are usually not considered. So we were lucky to be able to include transit, but traditionally transit is not included, but in general pedestrians are not included. And there are many reasons. It's much easier to measure vehicles and to detect vehicles than to detect people. So that's one of the reasons in terms of how you can collect the data and to integrate all these different databases. So in terms of other things, like say, we notice, for example, there are changes in air quality, but we don't know what is the actual impact in terms of health cost or overall impact on quality of life. So it's still, there are many, many unknowns, that things that people have to, researchers, and we need to work through in terms of really trying to connect all the dots in terms of improving traffic and improving using technology and to see the effects, just across not just vehicles, but also for pets, bikes, and transit. So I'm just including that because we are now doing a project where we're trying to measure, for example, what people breathe in terms of air quality and what we can detect from the breath sample in terms of pollutants that you absorb after biking in a busy arterial versus biking on a quiet bike boulevard. And we don't know the results because no one has done it. So we don't really know what is the time of exposure to bad air quality means in terms of the type of pollutants that you will be able to measure in your breath or your blood. So some lessons. It was key. We couldn't have done this without the support of the City of Portland and TriMet. in terms of providing the data and helping us to learn through the process, because it's not simple problems, so it's always good to get feedback and get good ideas from both of them. The value of data I think, is priceless, because again, if we want to ask questions beyond just the usual, do we have more capacity or vehicles going faster? If we want to know more about really what's going on with technology, is technology effective? Is it really improving quality of life? We need to integrate a lot of different data sources. And it's very challenging. And it's, all the GRAs are witnesses that it's not easy, because you have data sources that are totally different formats with different spatial resolutions. So some data could be every 5 minutes. Other data could be event-based, like the bus data. Other data could be collected for traffic purposes, like vehicle. Other data is from air quality. So just trying to put all that together to just run the models, it's very challenging and time-consuming. You need to calibrate devices. It takes a long time. So you are sure that you're getting good quality of data. And then, the time takes to clean the data, to validate the data, and so on. So it's not easy. It takes a lot of time to get the results. So the other thing is, as we are getting more data, and the problem, if we ask more sophisticated questions, then the models have to be more sophisticated. So if we want to, for example, understand how one bus is impacting the following bus, then we need to get into more sophisticated statistical models, looking at the correlation between the different buses, one with the other, with traffic, and so on. So there is this kind of increase in terms of complexity from the very simple questions to the more interesting questions that people would like to know in terms of how are things really, why things are happening this way, or how you can explain the complexity of the system. But the more you want to know, the more complicated it gets in terms of the tools that you need to get the answers. So, and I feel that's feeling how we feel after getting so much data, so many models. You just say, no, we get too much. I feel like the research assistants and I would sometimes say, it's nicer maybe to live in a world we don't know anything, and then the analysis is very simple. We look at before and after. But so ending some acknowledgments. I need to mention that the Oregon Transportation Center, OTREC, supported this research. So Peter Kunz and Willie Rotich from the city really helped us a lot, getting us access to data and also with feedback. The same, Dave Kraut, Steve Callas, and Curtis McCoy. So Dave and Curtis are here, so thank you very much for all your support. And then I mentioned that Courtney, Eric, Wei Feng, and Adam Moore, our research assistants. Thibault, a student from France, was also working on this for a while. Then we had other students that when we were doing data collection, Pam Johnson, Brian Davis, and Catherine Bell, because you need a lot of people to go with all the equipment, collect, so we needed a big team. And my colleague Chris Monsier and Christine Kendrick from Environmental Science were also part of this project. So we have some papers related to this. So we have so much data, we're able to produce several papers that I can later share with you. And I think it's hopefully I didn't talk too much, and I have time for questions. Just remember, use the microphone. Yeah.
Do you have any information or data on how SCATS or TSP affected pedestrian traffic?
We don't. I mean, we have some anecdotal evidence that because SCATS is responsive to traffic volumes during the peak times, the cycles tend to be longer, so pedestrians have to wait longer to get the pedestrian signal. So in a way, during peak times, it might be worse for pedestrians. But again, I don't have the kind of solid evidence to say that.
Hello. I have actually two questions, if that's all right. Was the data gathered for independent drivers on TSP usage for driver performance?
No. So we didn't get any name associated with bus drivers. We're just looking at was the bus late, how many stops, boardings, alignments.
Okay. And then the other one was, as for particulate matter, does the use of biodiesel decrease, increase, or was there no change in the amount of particulate matter?
Yeah. So in this study, we were not like, to know that, you need to compare, like, say, in a lab, an engine, and you put different type of fuels, and then you measure what is out. From the literature, we know that biodiesel sometimes can be produce more particulate, but again, the size and the distribution of this, there could be a lot of variation. But so the jury is still out there in terms of biodiesel and how much better or worse can be. And it can be better in some pollutants, can be worse in others. But again, we were not able to do that.
Okay, thank you.
Is the activation of the TSP, is that strictly controlled by the driver?
So no, the driver doesn't have to do anything.
Oh, just
so
automatically.
it's just, if the bus is late, then it's programmed that this emitter will be activated and will communicate.
Okay.
You got a slide up there about TSP, and you talked about there was a 90-second difference during peak time. Mm-hmm. What did you mean by that? 90 seconds per intersection, or what?
No, like overall, the travel time between, like, say, 86 and 10 during peak times can take like a minute and a half longer on average for buses to travel during peak times versus off-peak.
And then another question about the diesel particulate matter. You said heavy-duty diesel engines had up to 100 times worse particulate matter pollution. What do you mean by heavy diesel? Like a big pickup truck?
Yeah, so like, commercial vehicles, you see like, single unit or combination trucks or, buses and, anything that has a big diesel unit. But again, there is a lot of variation too, because it could be some very efficient diesel engines, and there could be some not really efficient. And like TriMet has filters, for example, that many commercial vehicles do not have filters. So, and it's expensive to add filters and, try to be clean. So in terms of, for example, improving the engine efficiency that, TriMet is really trying, you try to be more fuel efficient, then you tend to be cleaner in terms of air quality.
Thanks.
Now, I noticed that the use of both SCATS and TSP improved on time. Was there any data showing that there was any impact on overall driver safety, like total number of accidents, as a result of using either of those?
We didn't look at safety, and safety is very tricky because you need really long periods of time. Because if you're unlucky and there was an accident before and there is no accident after, there are so many factors related to safety that it's really hard to isolate what is the SCATS contribution to safety. Okay. So we didn't do it. But even if we tried, it's a very, very tough question to answer.
Sure.
On the slide where you talked about, the very first slide where there was a green chart and then a before and after SCATS chart, I didn't understand what the top green chart was referring to. It was a difference in speed, but...
The top green is just looking at the difference. So anything that was above 0 was positive speed. So basically saying that after SCATS, you get higher speeds. So this is go from 0 to, like, say, 10. So in these periods of time, on average, for example, here we detected that vehicles were going 3 miles per hour faster after SCATS versus before SCATS.
So on the bottom one, at one point after 8 o'clock, it's going slower.
Where?
On about 8:10.
Like,
Yeah. And then you look up.
so it must be a mistake in the graph.
Oh, okay.
So, yeah. Thank you for noticing that. But yeah, but be reassured that we did check the numbers, and on average, this was the case. Anything else? Yeah.
Two questions. The first, is SCATS still being used along Southeast Powell?
Yeah, so this is very expensive to install, and so once you have it, you want to keep it, running, unless you see that it's so bad. But in this case, because yeah, like yesterday they were mentioning, like, at least some of the wiring and equipment is like $50,000 or more per intersection, so it's not cheap. So.
Also, do you see this being effective in more pedestrian-heavy areas, like, say, Southeast Hawthorne or out here on Southwest Broadway? Would it still serve the same purpose, or do you think that it would be effective still?
So I'm borrowing, too, from yesterday's discussion about SCATS. In general, if you don't have pets, it's better for SCATS because there are less constraints, and you can just optimize for vehicles alone. If you have a lot of pedestrian calls, and you need, especially you have wide street, pedestrians need a lot of time to cross. Yeah? So then you kind of, in a way, get all the system off sync in terms of coordination. So you will tend to see that with a lot of, in downtown areas with a lot of pedestrians, the gains might not be as much as in a more suburban area with less pedestrian calls. Especially, again, if the streets are very wide, then because every pedestrian call might, stop the green for a long time on the main. So,
Thank you.
There is an online question that's related to the last question. Are you in a place to evaluate the cost-benefit efficiency for the SCATS, given that the benefit is here? And
sure. So that was not part of our project, and it's something that we were able to do, but I think it's something that can be done, but it will require input from, like in this case, Pivot in terms of staff time, because it's not just equipment and you install the equipment. It's like throughout the life of the installation. If there are, for example, you save on staff time in terms of updating the traffic signal timing and so on. So I guess it's something like maybe we need more time to see over time and compare the before, 2 or 3 years before versus 2 or 3 years after in terms of how much time it takes, because it takes a lot of time to calibrate the system. But then once you get to that sweet spot where the system is working well, it takes less work. So I think it's maybe too early to do that.
there is another online question regarding measuring air quality. Have you been able to tease out other factors like climate, wind, like wind temperature, humidity, and direction, and some other?
Yeah, so atmospheric conditions are huge impacts. So, and the results I was showing was like controlling for those things. So, but temperature, humidity, wind speed, wind direction has a huge impact on the air quality at the given location. And air quality is really, really tough because you cannot measure everywhere. You have just limited equipment, and you need to choose just some locations. But we're able to obviously control, because we have anemometers, and we're measuring temperature and wind speed and direction second by second. So taking that into account, then we can see what are the effects of the green times and vehicle volumes and type of vehicles, diesel versus gas vehicles and so on. So yeah, maybe I didn't mention that, but that's why air quality was at the end, because it's so complex. You need to take, I think Carney Slavin was working on this. I think there was a time we had 150 variables in our model. So we didn't have room to really put so many, because it's not just what's happening at the time. You also have this lagged effect you need to look at now and 2 minutes before, because maybe some vehicles that were present 2 minutes ago are impacting still their quality at the moment. So it's a really tough and complex modeling for air quality.
Okay. Any questions here? We have time for one last question.
Yeah.
Over what months of the year was your data collected?
So SCATS was implemented in the fall, around October. So that was one of the things, like we didn't have like perfect data in terms of before and after. So for example, for the bus, we collected data. We got data like say 1 month, like say in, so I think we used July and April, and then we gave some couple of months after, like say April, May, later, to SCATS also to be calibrated and to be working. So, but we took into account again passenger boardings, weather, time of the day, and so on. So it was not perfect in terms of if we have to do it again. It's always nice after we learn how to do the challenges. We were able to collect better and more data before, because now we have a lot of data for the after, but we don't have so much for the before.